do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And my special business today is this subject: the transfer of heat energy by the mechanism of conduction. Conduction. Very important word to know the meaning of. And I invite you to look it up because its Latin origin is very important. Conduction. Consider the following: an experiment which we will imagine. Here are two rods. One is copper and one is iron, and they are fixed together very tightly at one end. And I am imagining that I am doing the classical experiment that Ben Franklin did on his investigation of heat transfer by conduction. We will imagine that I put this junction in a pot of hot oil, just like that. And I hold on to the remote ends of the bar as I am doing. And lo and behold, in a short while, a strange thing is witnessed. One of these feels hotter than the other and sooner quicker, which means that one had thermal conduction at a greater rate. I invite you to do this using a pot, say, of boiling water, and you will find a strange thing, that the conduction along copper is about 10 times as fast as along iron of the same size rod. Consider another wonderful experiment. I'm going to light my gas burner here, which perhaps I should have done already. There's the burner. Now what do I have? I have two rods, a shiny metal one and a wooden one, tightly fitted at a junction here. Now, around that pair, I have put a sleeve of paper. Here is a wooden rod, there is a metal one, and I've put that sleeve of paper tightly on that junction. And I'm going to put this junction in a flame of a gas tank, gas burner. And a wonderful thing will happen if it does as I want it to do. And if it doesn't, well, then somebody says, "Oh, Professor, the experiment failed." But experiments do not fail. I must provide nature exactly as she requires, or she won't do what I want her to do. I'm going to do it. And watch now. Watch a wonderful thing. A little. Yes, there it is. There it is. I want the camera to get it tight. Do you see a very clearly bounded line? Beautiful. And what do we find? That paper scorched on the wood side, but not on the metal side. Why? Because the metal is a good conductor, and it took the heat energy away and did not allow time for the paper to scorch. Now, next beautiful thing. Here is a little paper cup. I'm going to put a flame under that paper cup, and as anyone in his right mind would say, "Professor, that cup is going to burn." Of course it's going to burn. There it is. It's burning up. It's burning up. As one would say, its kindling temperature was raised. No hurt. No hurt. That's a pretty thing to see, though. I like that. Look how nice and shapely it still remains. Now what am I going to do? I am going to fill another identical cup with water. I'm going to fill a very same cup with water. There it is, right filled. And I'm going to put this flame under that cup. And imagine what we will witness. We will witness this, that water can be boiled in that cup without burning the paper cup, except at the rim where the paper is doubly or triply folded and therefore very thick. So let's go on with some other matters while we are waiting for that. Notice, the housewife does not have to have metal dishes to cook in. She can cook in a paper cup, which is an idea for conserving or conservation or something. Let's look at that. Let's look at that again. That water will shortly be boiling, and I can boil the water away without burning up the cup. Question regarding a thermometer. Notice, thermometer. Yes, that's what it is. I have a thermometer. Question. Supposing I had here a glass of very hot water. Let's imagine. You see, imagination. I must emphasize that again, wherever is my pen. Imagination. A very necessary ingredient of your life and work, especially if you're going to be a physicist. Here is a thermometer. There is a glass of hot water. The thermometer reads the room temperature at this moment. Question. I submerge it quickly into that glass of hot water. What do we see first? Very quickly first. Answer. not usually given. The answer is this. There is a drop in the reading of the thermometer. It reads less. Why? Because the glass bulb was heated first by immersion in the hot water, the glass bulb expanded, and the mercury level dropped. But now, after a while, when the heat energy has been conducted through the glass into the mercury, then up goes the level. One other question while I'm on a thermometer. Why is the bulb cylindrical instead of spherical? Why is it cylindrical? Very good question. So you notice my philosophy here, people, teachers, mothers, fathers, young and old, children, students. Not to teach you any physics, but rather to show an abundance of demonstrations which are enchanting and dramatic to witness. Let me consider, oh, look here. Let's look at that again. The water is boiling fearfully fast, bubbling away, and yet the paper cup remains nearly with immunity. Let's go on. Here I have a cigarette. Let me light this cigarette. Notice I don't know which end to light, but I'll light a cigarette. Now, I have done this already. I laid the cigarette on this wooden block. And do you see what happened? The wooden block got scorched. We don't use wooden blocks for for ashtrays. We use glass for ashtrays. Why? Because when the cigarette, if left to its own, forgotten, let us say, when the burning gets to the glass conducts the heat away, and the cigarette probably will go out. Let me illustrate that. Here is a beautiful demonstration for you to do. A fork and a spoon, which I lodge together in this manner, and then I'm going to put a match there. Notice I'm trying to work fast and probably will get it all fouled up because I'm working fast. And here is another match, and watch what I'm going to do. Watch. That's a beautiful thing. Notice how stable that is. That's terrific. If we can get a tight shot right on that. Now I'm going to light both matches. Just give me your attention a minute. I'm going to light both matches. Question, what will happen? Answer, I suggest nothing will happen. Why? I'm sorry. I blew out that match, and I shouldn't have done that. Watch it. Both matches will go out. Why? This one will go out when the flame reaches the glass, and that one will go out when the flame reaches the spoon. Well, I hope it doesn't work. And then you'll say, well, it did. Just give me your attention, boys and girls and ladies and gentlemen. Do you see? It nearly didn't do what I wanted it to do. And I urge you, well, it didn't do what I wanted it to do. And I don't want you to say that the experiment failed, because it did not. I did not make the necessary provisions for nature. All right. Next question. Beautiful for the housewives, children, mothers, fathers, teachers. Here are some small potatoes. Let's imagine we have put them in the oven to bake, and they are nearly all baked. Dinner is about to be served, and knock, 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 some company, unannounced and maybe unwanted. You have to bake some potatoes quick for them, and all you have are some big ones. Now, you know these will take very much longer to bake than these small ones. You are not allowed to cut these, but you want them to bake quickly. Question, how will that be done? Wonderful. Just take a couple nails like this, 80-penny spikes, bang like that, and bang like that, and 2-3 more, and put them in the oven. And are we not agreed that the thermal conduction of this iron nail will transfer the heat energy to inside the potato, and it will bake with all quick dispatch? Right. Or, again, for people who eat, flesh eaters, carnivorous human beings. Question, let me imagine that I have 2 identical roasts of beef, absolutely identical in every respect except that one has a bone in it and the other does not. Question, what is their rate of cooking when put in the oven? Answer, the one with the bone obviously will cook the faster for very obvious reasons. is not bone a very good thermal conductor? Indeed, it is. Apart from that, I would like to lecture for about a half an hour on the beautiful virtues that this bone possesses. Inside, for example, the marrow, a blood factory which keeps us going. Wonderful thing. So think more about the virtue of a bone. Or consider this. Ho, ho, let's get back on there. Let's get back on there. Camera, quickly, get on the water in the cup. The water is nearly all boiled out, and the cup is still not burning. And I say that's remarkable. Or, give me your attention for another dramatic experiment. Here is an asbestos glove. Notice. Notice. With absolute immunity. Why? Oh, I'll let that go, because when all the water is gone, the obvious consequence must ensue. The paper then will reach its kindling temperature and conflagrate, as one would say. Another wonderful demonstration, thermal conduction. Imagine that you get up in the morning, put your feet out of bed, and put your feet down on the floor. Do you not prefer to put your foot on some deep, heavy, matted, stranded woolen rug rather than on a bare floor? Obviously. Why? Consider the following. Here I represent a bare floor, and here I represent a deep knitted rug, a braided rug. I'm going to do as follows. Right here and now, feels cool. Oh, that feels warm, when in fact they are both at the same temperature. But this conducted the heat away at a much more rapid rate, and therefore it felt cooler. More than that, illustration. When you get up in the morning, if you don't have a rug near the bedside, what do? Don't you turn your footsie-wootsy on the side, sort of? Why? To make less area of contact, so less heat energy will be conducted away. The same thing happens here. I have a metal faucet. I have a tabletop. I put my hand on the tabletop, feels warm. I put my hand on the faucet, feels cold. Oh, no. They are the same temperature. This, however, is a good thermal conductor and took the heat energy away. Another remarkable demonstration. Here it is. Let's see. Oh, yes, notice. I'm going to show you. The water is nearly gone, but the paper cup is not burned. Let's get on to this one. Here is, no, I can't do it, I don't think. Here is a hub with some metal spokes, all different materials. If I heat the metal hub, would I not find that the different materials conduct the heat away at different rates? So our show has been on the transfer of heat energy by conduction, and I thank you for watching.